Hello and welcome to Aerospace and Mechanical Lab 1. Today we are going to talk about Lab 2, Bending and Torsion and Strain Gauges. In today's lecture, we are first going to talk about designing an experimental test. Essentially, we are going to introduce the standards that we have in our disposal to design a test to measure the modulus of elasticity of a beam, for example. And these tests are called ASTM standards. We will talk very briefly about these type of standards, and then we will move on to the bending and torsion review, the theory review of bending and torsion, and then we will move on to watching a couple of videos about applications of bending and torsion analysis. And for the second part of the lab, we are going to move on to strain gauge and data acquisition, systems and devices, and eventually we will talk about the lab itself. You want to keep in mind that for this lab, you need to write a full lab report. It is not a worksheet anymore. Okay, so first question I want to answer is how we can design an actual experimental test. What are the tools we have in our disposal? Like, specifically, we want to focus on a flexural rigidity of beams test, essentially a test that is going to help us understand the bending of beams specifically. Or we can definitely use these standards to design any other mechanical test that we want to perform. Just have to find the appropriate standards. So ASTM standards are introduced to help us build tests for specific purposes, bending, tensile, different types of mechanical tests. ASTM itself stands for American Society for Testing and Materials. So essentially any test that is related to the strength of material, mechanical properties of material, or any other properties of material can be found in these standards. And the idea is they have introduced standards to make sure that everyone all around the world actually uses the same procedure to make the measurements of, again, modulus of elasticity or deflection of a beam, for example, or the strength of a concrete beam, for example. So we can compare the results of these tests with each other throughout the world. So the idea is pretty simple. If you follow a standard, everyone can look at your results and understand your results easily. Right. The standard we have that we're going to use for this test that we're going to run here is very similar to ASTM C1609, essentially a 3-point bending standard. I'm going to play this video for you. And this video is going to be posted on the Blackboard anyway, so you can definitely watch it.
Expert 2655 dual column electromechanical test machine.
Okay, so as you can see here, we have a load cell, and in this load cell we have 4 essentially contact points. 2 of these will be supports for the concrete beam they have here, and two of them are going to apply the force. I'm going to move on a little bit so you can actually see how the force is applied. This is where the forces are being applied, and these are the 2 supports. So this type of bending scenario is called 4-point bending. Pretty simple. We have 2 supports, 2 points at which we are exerting the force. This 4-point bending can help us understand the strength of concrete in this specific example. The test we run in our class, though, is going to be a 3-point bending test, and we are going to use a gauge dial to measure the deflection of the beam. So everything will be analog. There's nothing digital involved in our bending and torsion test, at least for the first part of the test. Okay. So let's move on to bending. We understand the standards now. We want to understand what type of test we're going to run and what are the equations we need to use to analyze our data, essentially. Before starting the theory, we first need to understand what bending is. Bending happens when beams are subjected to equal and opposite couples and acting in the same longitudinal plane. So essentially, when you are, an example of this is someone trying to lift a weight, right? Pretty simple. We are going to have an exact equal and opposite couples essentially by the weights that are being exerted. Right here is an example directly from the Mechanics of Materials book. We have two couples, opposite couples acting in the same longitudinal plane, and this is going to cause a deflection in the middle. Like the middle of the bar is going to go up. This sort of scenario is called bending of beams. Right? And the equation we use to analyze the bending of beams, this is the differential equation, is essentially has flexural rigidity modulo elasticity multiplied by the moment of inertia multiplied by the fourth derivative of deflection at any point on the beam with respect to the location on the beam to the fourth. And all of this has to be equal to the load that is being applied. This load can be a distributed load or can be just one load that is applied in anywhere on the beam. Okay, moment of inertia, as you saw in this equation, plays a very crucial role in beam analysis. You can see it is actually right here directly, and is contributing to the flexural rigidity of the beam. Why the moment of inertia is important? I have this 4-minute video right here.
Shaped like an eye?
I am going to just play it for you so you can watch why the I-beams are important, and you can always go back and watch it on Blackboard yourself whenever you are going through the lecture slides.
But after asking some of my friends, few actually knew the answer to this simple question. The I-beam is designed in that way to handle a maximum bending load while using the least amount of material. Let's look at an I-beam supported on either end to understand more. When we apply a uniform load across this beam, the max deflection will occur here in the middle. We can calculate the deflection with this equation. This may look complicated, but it really isn't. W represents the uniformly distributed load in terms of newtons per meter. L is the span between supports. E is the Young's modulus, which, as explained in my Material Properties 101 video, describes the stiffness of the material. But the variable we want to focus on is I, which represents the second moment of area, sometimes called the moment area of inertia. This describes the shape of the beam. More specifically, it describes how the material is distributed throughout the shape. These two shapes have the same area, but that area is distributed very differently, and that is very important. A seesaw is a good analogy for this idea. When we place weight in the middle, it is very easy to lift. In fact, if we place it exactly over the middle, we aren't lifting it at all. But the further we move that weight to the end, the more difficult it is to lift, due to the increasing leverage. A very similar thing happens with beams and bending. Material at the center of the beam, which is called the neutral axis, does not resist bending, and the material furthest away from the center resists bending the most. It is called the neutral axis because if we place a bending load downward, the same way we did before, the beam will bend in a way that will cause the lower edge to be in max tension and the upper edge to be in max compression, and the values of stress gradually decrease to zero at the neutral axis, where there is neither tension or compression. Because the tension and compression is maximum the furthest from the neutral axis, we want to maximize the amount of material on the outside of the profile, where it is needed most. The more material further from the neutral axis, the larger the second moment of area will be. Applying that to the equation, we can see that a larger second moment of area would result in a smaller deflection. So if we place this section under the same bending load, it would actually be stronger if we flipped it over 90 degrees, because now more material is located further from the neutral axis. We could make it even stronger again by reducing this thickness to a minimum, just enough to resist the shear stress, and placing that material at the top, and suddenly we're back to the I-beam shape. You can see this idea put into action all around you. In my last video, I mentioned just one of them when I spoke.
Okay, so hopefully you understand now why I-beams are better for bending resistance, right? And in this test, in our test, we are going to actually put this idea to the test. So we are going to do a 3-point bending test in the lab. A three-point bending, it pretty simply means that we are going to apply one load in the middle, and we are going to have two supports. We're going to test two different types of supports. One is simply supported beam, and one is built-in beam. So built-in beam, essentially you have fixed supports where there are no rotation and there are no translation. Simply supported beams can tolerate translation. And the way you do this is pretty simple. Just essentially loosen the support a little bit. You can watch the video that we posted later on the lab itself to understand how we can actually do this test. So we are going to apply a load and measure deflection. Okay. The next thing we are going to analyze is torsion. Torsion is essentially when you apply torque to twist a structure like this. This is where the torsion deflection happens, right? In actual loads, we are going to produce a uniform stress over the cross section of the object. But the torque is going to create a distribution of a stress. So essentially that is the main difference between an actual load and a torque or a torsion scenario. Torsion itself is very applicable in aerospace industry specifically. We can see this in torsion boxes. Torsion analysis needs to be done for torsion boxes that are used to minimize the deflection in the wings of aircraft. So whenever you see actually a buckling or bending scenario in any of your designs or structures, you definitely need to do a torsion analysis. Okay. And the equation for torsion is pretty simple. We have T, which is the torque that you're applying, divided by J, which is the polar second moment of area or the polar moment of inertia, multiplied by modulus of rigidity, which is essentially the counterpart to modulus of elasticity in angular deflection scenarios. Then the angle of twist, which is the amount of angular deflection that we'll see, divided by the length of the beam. This is also equal to shear stress divided by the radius of the beam. And in the test that we are going to run, we are going to use this equation specifically to do our analysis. But the idea of the test is really simple. You are going to apply a load. You know the shaft length. You can calculate the second moment of inertia, the polar second moment of inertia. You can measure the angle of twist, and you have to find the modulus of rigidity for the specific beam you're using. Bending and torsion have a lot of applications. We are going to watch a video about a specific application, bending and torsion test specifically, that is actually very useful. Whenever they design an aircraft, they need to do a bending and torsion analysis on the wings of an aircraft. This is a real bending and torsion analysis. As you can see, there are mechanisms that is going to help. Let's wait right here. As you can see, there are mechanisms. There are rods connected to these I-beams that are applying the load. The reason we have these I-beams is because we want to simulate the uniformly distributed or non-uniformly distributed load that is being applied to the wings here. So that's why we have the I-beams, and that's why we have different levels of it. This is essentially applying distributed load. As you can see, it is creating a deflection to making sure that the wing of an aircraft can actually resist the force that is being exerted by the wind. Okay, so let's talk about the test that we are going to run. For the bending part, we are going to use 3 different types of beams. We are going to use an I-beam, we are going to use a regular beam, and we are going to use a hollowed beam. The difference between these 3 beams is in their moment of inertia. The moment of inertia equations here are given to you. So we have the moment of inertia that is given to you, and you can use this to do your calculation. But the equations that we are going to use here are, for beam is a simplified equation. Bending is a simplified equation. We are only interested in the deflection in the middle. We are only going to measure the deflection in the middle of the beam. So we are only interested in the maximum deflection, because that's where the maximum deflection, when you apply load to the middle, the maximum deflection happens in the middle of the beam. For the simply supported beam, the maximum deflection can be calculated by this equation. W is the load, that is the point load you are applying, multiplied by L3, which is the length of the beam, divided by 48, multiplied by the flexural rigidity of the beam. For the built-in supports, the maximum deflection is a little bit different. The equation is essentially very similar to the previous equation, but the value we have in the denominator is going to be 192. This is going to tell us for the built-in end beams scenario, we are going to see a smaller maximum deflection. So the idea is you are going to put this beam in, you are going to apply some loads to the beam, change the support, apply the same loads, and during all of this you have to measure the deflection of the beam. And for the torsion part, the same scenario, you're going to apply a load to two different beams here. One is a hollowed out beam and the other one is a solid rod, essentially. And then you measure the angle of twist, you know the torque that you're applying. You can do the calculation for the modulus of rigidity of the beam. This is how the setup is going to look like. This is the bending scenario. We're going to see that later on in the recording that I'm going to make for the lab itself. We have load being applied in the middle. You have a dial that is going to measure the maximum deflection, and these are the two supports. If you loosen the two supports, you're going to get a simply supported beam. And this is our torsion mechanism. We essentially have a arm here that is going to help us apply torque, and we have a very small device here that is going to help us measure the angle of twist. You want to keep in mind that this is an analog measurement, meaning that the uncertainties are going to be pretty high. You want to make sure that all of these supports are very tight, especially for the torsion scenario and the built-in beam scenario. So there is no slippage. Again, especially in the torsion scenario, you want to avoid a slippage. You're going to see more of this in the video. But the idea is we are going to understand the importance of material properties, modulus of elasticity and rigidity, and the moment of inertia in maximum deflection and the maximum angle of twist. All of these tests must be done at least 5 times. And by 5 times, I essentially just mean we need 5 data points for the modulus of elasticity measurements at least. But you're already covering these 5 measurements simply because we have 3 beams, 5 loads that you're applying to each beam, and 2 different scenarios. So you have essentially 30 different measurements for this, and we have a couple of different measurements for this, the torsion one as well. You want to make sure you calculate the uncertainty of these measurements too for the modulus of elasticity and modulus of rigidity calculations. If you are not given a confidence interval, you are welcome to use the confidence interval of 75% for your measurements. And you want to keep in mind that we want you to use the student t-test for all of these analysis. Okay, so this is it for the bending and torsion scenario. This is it for the analog part of the lab. We are going to move to the digital part of the lab. Essentially, we want to understand how digital sensors and how DAQs work. First of all, you need to understand what a sensor is. Sensor simply is a device that responds to a physical stimulus. It can be any type of physical stimulus. In this specific scenario, we are only going to see a strain, essentially the deformation of a beam, right? And that deformation of a beam is going to be transferred to a computer using the sensor that we are planning to use. The sensor we want to use for this purpose is called a strain gauge. A strain gauge is made from thin wires. As you can see, these are the thin wires that we see that are bent from a parallel sensing loop, right? And they are glued on top of a very special back paper to make sure that it is electrically isolated, because we don't want these wires to have any electrical connection to any other surface, right? And again, as the deformation happens, these wires are going to stretch, get closer to each other, or get further away from each other, and that is going to change the current and the resistance of this loop, which eventually is going to change the voltage that you are going to measure. Eventually, we have different types of strain gauges. The modern ones use conductor foils that are glued to a flexible, non-conducting thin films. We have a lot of these strain gauges in the lab. If you are interested in learning how to install them, you want to reach out to your TA or me, and we can definitely get together one day and install a strain gauge. Okay, so another look at a strain gauge. You want to make sure when you are designing and creating a strain gauge, you want to make sure that each of the strips is minimized to essentially minimize the transverse strain. We have a strain in this direction, deformation in this direction, you will see a deformation in this direction. And we want to minimize that. We don't want to actually see any effect of that in our strain measurement. And then we can measure up to 10% strain in our devices. This is right here. We have a real strain gauge. As you can see, we have two wires coming out of it that's going to connect to your computer, to your DAC. And this is a strain gauge, as is the wiring itself. Installation is pretty simple. You just have to make sure you clean the surface as much as possible, and then you use a special type of glue to install it to any surface that you want to install. Strain gauges themselves are pretty robust. They, as long as you don't really break the wires, of course. Okay, they have a lot of applications. You will see strain gauges everywhere if you actually look closely for them. We can have different types of sensing. We can have wired sensing, which is what we use in the lab. Essentially, these wires are going to go into a data acquisition device, which we are going to see later on. And then that data acquisition device is connected to your computer that is going to help you convert the signal to a strain values. But we can also transfer the data wirelessly, as you can see here in this specific scenario. Again, working principle is pretty simple. You change the electrical resistance of the wire by the deformation of the system by the deformation, and it will change the voltage that you're reading. And that voltage can be correlated to a strain based on the base values for your strain gauge. Again, we're going to see more of this in the recording of the lab. In the lab itself, you are going to given a beam that is installed in a cantilever beam position, meaning that we have a fixed end here and we are applying force in the middle. We have a load cell right here, installed right here, that is going to help you measure the applied load. And then we have installed a strain gauge right here that will help you install the strain. So using the load here, you need to find the stress at this specific point and then relate the stress to a strain for that specific point. And and find the Young's modulus. In a lot of our mechanical properties tests, the goal is to find the Young's modulus, or the modulus of elasticity of the beam. And we want you to do this test with 95% confidence. And since you do have to do a statistical analysis, you need more than one data point, which essentially means that you can just apply different loads to measure different strains. You want to keep in mind that the strain gauges need calibration, and we are going to talk about all of those and the wiring of strain gauges in the recording of the lab. Thank you for watching this recording. Please let me know if you have any questions or concerns.